first proper session of the Open Day. I'm delighted to welcome Cory Benfield, who is one of our organisers at Pycon UK. He's been speaking at the conferences for several years. He's very active in open source, and he's a nice guy. He'll tell you more about what he's talking about. If only everything were radioactive. Cory.
Okay, first question is, can everyone hear me fine? My mic level's good. Thumbs up from the back. Awesome. Hello, I am Cory. I'm going to do a very quick introduction to myself because I have nowhere near enough time. And I'm going to apologize to the speech-to-text people because I'm known to speak very, very quickly for 20 minutes. Sorry. I'm an open source software engineer. I work for Hewlett-Packard Enterprise. I work in HPE's kind of upstream open source team. This is a team inside HPE that's focused on the continued good health of open source software ecosystems that are really important to our customers. So we sell them a whole lot of kit. They want to run open source software on it. We want to make sure that it runs as well as it probably can. And that is where I work. If you are interested either in shouting at me or finding out what HP pays me to do, these are the two best places to find me. I am reasonably responsive on Twitter. Please direct all your hate mail there. I am reliably informed that Twitter is the venue for hate mail. Please send it there. And then I get to do all of my work on GitHub. So you can go take a look on GitHub to see where I am spending HP's money, basically. All right. So I do a whole lot of open source stuff, and we're going to talk about none of it. Instead, I want to talk about an interesting idea because this is the Open Day session, and I'm acutely aware that we're going to have a lot of non-specialists in the room. So instead, I want to talk a little bit about randomness and randomness in computing. I have 20 minutes to talk, which is not very long. So I am not going to I'm not going to go into detail on anything. I'm going to skim very lightly off the top of one of the most complicated subjects in computing. There is a lot more detail. If you are here for the whole conference and you want some more detail, I am giving a second talk on Sunday, which will logically follow on from this talk a little bit. I'll focus on some other material. So my plan is, I've got 2 bullet points. We're going to talk about what randomness is, and then a little bit about how we use it in computing. So, what is randomness? I don't know about the rest of you, but I'm a millennial, which means I have only one way to solve this problem, which is that I use Google. And I'm a software developer millennial, which means that I use Google very effectively because I know all the magic words. So we're just going to ask Google for a dictionary definition of randomness. This is what I would do. There are lots of parts to this, but this is the part we care about. Google defines random as governed by or involving equal chances for each item. Okay. I mean, that's fine. That's not obviously wrong, but it does seem kind of crucially incomplete, right? There seems to be some stuff missing from that. And by way of example, I'm going to use the only slide of code in my talk. I apologize for anyone here who does not read Python. I will explain this to you. But this here is a function called randrange. Randrange is a pretty common function. It's defined as, ordinarily would be a function that returns a random number between its start and end points. Because I don't care about API compatibility, this is actually a generator that returns a sequence of random numbers between its start and end points. Now, if you iterated over this 10,000 times and you got out 10,000 numbers from this, and then you plotted how likely they were to come out, you would find that every number within the range of start and end comes out exactly the same number of times. They have a perfectly equal chance to come out of this generator. But I don't think anyone in this room would claim that the numbers this produces are random. They go in a sequence. They go from 1 to 2 to 3 to 4, and then back to 1 to 2 to 3 to 4 to 1 to 2. So there is something crucial missing from the definition of randomness if you can call this random. I don't think anyone here would want to call it random. I certainly wouldn't. So I think we need to add something else. I'm going to say that the key additional property that Google was missing is that random numbers, and particularly sequences of random numbers, should be unpredictable. That means that if you've got the last random number I generated in your hand, you should not be able to tell me what the next number is going to be. So this is key. It's not enough that a source of numbers be evenly distributed. Lots of sources of numbers are evenly distributed, but in no sense random. They are entirely deterministic. So a good source of random numbers generates unpredictable ones, numbers that you cannot guess with any better probability than 1 over whatever the size of the range is. If you're generating random numbers between 1 and 20 inclusive, you shouldn't have any better than a 1 in 20 shot of guessing what the random number is, no matter what's happened. For people in here who like math, we could say that the outputs have low correlation. That's great. So that's all I need for the definition. Where do they come from? Where do we get random numbers? Like everything in randomness, the answer to this question turns out to be a little bit subtle and boils down to, do you want true randomness or good enough randomness? I appreciate that answer is not that helpful, so let's talk about a little bit what I mean. True randomness can be thought of as a form of randomness or a source of random numbers that is derived from a physical process that we, the physics community, the wider physics community, truly believes to be unpredictable. That is, the process itself cannot be very effectively predicted by a physical model. Numbers sourced from true randomness like this are genuinely unpredictable. They are unpredictable in a kind of profound philosophical way that makes theoretical physicists and computer scientists very happy. Now, they're not necessarily evenly distributed, interestingly, but usually you can apply some kind of mathematical transformation to make them evenly distributed. These mostly focus on unpredictability. Now, I appreciate that that's a deeply unhelpful definition. I've just talked a whole lot and waved my hands, so I'm going to give you some examples of sources of true randomness. The kind of example, and the most obvious one, is fair dice. If you have a human being throwing a fair dice in a normal room, that is about as close to a true random number generator as anyone can easily lay their hands on. There are all kinds of caveats to this. If you get a robot to throw a fair dice in a vacuum, that robot can usually reproduce its rolls pretty effectively. But a standard human being doing standard dice stuff, playing a board game or whatever, they're an excellent source of random numbers. There are some other good ones. Comfortably the most awesome one is atmospheric noise. Atmospheric noise is noise in the radio portion of the EM spectrum, just random noise that comes from, and I'm quoting the Wikipedia definition here, atmospheric stuff. The best form of atmospheric stuff is, as it turns out, lightning. Lightning strikes around the world produce noise in the radio portion of the EM spectrum, and you can use that to generate random numbers. That's excellent. That's very cool. There's even a website online that claims to give you random numbers generated from atmospheric noise, though I should clearly point out that it's just a server somewhere on the internet, so who knows if that's what it's actually doing. And if there are any physicists in the room, there is one that they've been wondering why I haven't mentioned, which is radioactive decay. Quantum mechanics is one of the few areas of physics that is explicitly dealing with things that are statistically predictable but individually unpredictable. And radioactive decay is an excellent example of this. If you've got a whole lot of radioactive atoms all floating around, they have a probability to decay, and their probabilities are entirely independent. So when each one decays, it's unrelated to when every other one decays, and you can use this to create yourself the world's most deadly random number generator. Now, there's a problem with all of these, which is they don't fit into computers very well. It is quite tricky to create a small cloud with lightning strikes inside your computer. It is even worse to mount radioactive things inside your computer. Not that we don't do it, we just don't tell you about it, but it's a bad idea. And generally speaking, of course, we don't have access to these sources of things in your average computer. For the computers in this room, all of which I guarantee to you are generating random numbers right now, none of them are using any of these processes. So instead we use things that we believe are random enough. And this is a hand-wavy definition too, but there are two major sources in computing for these. The first one is network packets, arrival time of network packets. We have a whole lot of laptops and phones in here, all of which are connected to the Wi-Fi, and they're all emitting and receiving network packets all of the time. Generally speaking, the specific arrival time of those network packets is unpredictable. And by specific arrival time, I mean the low bits, like what nanosecond of a given second were they received on. These things are largely uncorrelated and unpredictable, so we can use them as a source of random numbers. Not very much random numbers, that each of those events produces very little randomness, which we call entropy. I'm never using that term again in this talk. We call it entropy. You can use the least significant bits of that timestamp to produce a little bit of it. Another option is hard disk seek time. If you ask your hard disk to read block X, the hard disk has to spin a thing and move an arm and do some stuff, and that takes some amount of time. Again, the least significant bits of that time are largely pretty random. Note that this doesn't work if you don't have a hard disk. If you've got solid-state storage or flash storage, this doesn't work, and don't try to use it, because the seek time on these is extremely uniform. It's just not going to work even slightly. And there is a third source that is common in this room, and that is to have the chips embed some electronics that produces randomish numbers. This is from an iFixit teardown of an iPhone 6, 6S. I don't know their generations. But on the secure enclave portion of their little chip, Apple have mounted what they call a true random number generator, which is based on what's called a linear, free-running oscillator. I apologize, free-running oscillator. I have no idea what this is. I'm not going to go into it. But this is a small source of random numbers on every phone. My question to you is, why did Apple bother? What's the point of putting free-running oscillator into this chip? Why did they do it? I'm going to answer my own question because I'm a good speaker, and I was told that rhetorical questions are important. And there is a problem, which is that if you have no clouds in your phone and you have no network in your phone, then you have run out of sources of random numbers, right? If you took your phone right now, put it into airplane mode, then we can't use the arrival time of network packets because all your radios are off. You've got no cellular traffic, you've got no Wi-Fi traffic, you've got no Bluetooth traffic. And you don't have a hard disk, so you can't use its seek time. So you are officially out of sources of random numbers. Even if you weren't, the other sources of random numbers I just mentioned provide, at most, a few thousand bits a second. For the purposes of my analogy, I'm going to say 1,000 bits of randomness a second. Now, if you were using this in, say, a web server to create web connections, you need to encrypt them. You need to use HTTPS. And each HTTPS connection has a session key, which is 128 bits long. And we would like that to be random, because if it's not random, people just guess. So we want it to be random. So you need 128 bits of random for each inbound connection, and you've got 1,000 a second. So how many connections can your web server take a second? The answer is 8. And anyone in this room who has ever actually run a web server would know that 8 connections per second is utterly unacceptable. They would get fired if their web server only allowed 8 connections a second. It's a terrible, terribly low number. So, sources of random numbers are a problem. Frequently, in computing, you need thousands of random numbers a second, thousands of random long numbers. We may need kilobytes of random numbers every second. This is particularly true if you're running a video game or a scientific simulation. They need loads of random numbers. And there's just not enough from any of these sources to use. We can't use them. This means, in practice, most computers don't use these sources directly. They mix these sources into something else. And that something else is called a pseudo-random number generator. This is the solution to the I don't have enough randomness problem. This is a terribly long name, so you will frequently see it abbreviated. It will be abbreviated to PRNG. I could have asked you to guess. It's not a difficult abbreviation, but it's good to know. PRNG, pseudo-random number generator. Now, pseudo-random number generator is a fun name. I like the word pseudo. I want it in more things. And it's right, fun to spell. You'll get it wrong a couple of times. It's good. But it's not an explanatory name, right? What's a pseudo-random number? Does pseudo-random affect number or number generator? There are some ambiguities around this name. So I'm going to tell you that they also have a different name. And that different name is Deterministic Random Bit Generator. This is also a long name, so we also abbreviate this to DRBG. But this name raises much more interesting questions. It's got the word deterministic there, right next to the word random. That is odd. How can you have a deterministic random anything, right? So to answer that question, we're going to have to talk a little bit about what a pseudo-random number generator is. And at its core, a pseudo-random number generator is really easy. It's just an algorithm that takes some initial input, called a seed, and generates a very long sequence of outputs from it. Right? This is not that complicated. Generally speaking, when you're using a pseudo-random number generator, your seed will be truly random. You will have grabbed it from any kind of source of true randomness you could find, network packets, lightning strike, whatever you can do. Seed it with that, and then you run that forever. The much longer sequences of numbers that the pseudo-random number generator produces should be approximately random. Generally speaking, when we're talking about this, approximately random means passes a statistical randomness test. But you would be surprised how many pseudo-random number generators don't pass statistical randomness tests. That turns out to be a tricky bar to leap. Now, of course, I said approximately random. Everyone in the room is sitting there going, it's not random at all. Algorithms are totally deterministic, so a pseudo-random number generator is totally deterministic. You give it an input, a whole lot of outputs fire off, bang, 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 but all of those are determined by the algorithm and by the original seed input. So yeah, they're not random. At a philosophical level, there's no randomness here. But they appear to be random. Like I said, they pass statistical randomness tests. They are random-ish. And a good pseudo-random number generator is very random-ish. I'll get onto that in a little bit. There are bad ones. I'm going to not talk about them too much. They are relevant. They'll come up again in the future. But for the moment, not talking about. So this gives pseudo-random number generators some interesting properties. For one thing, they're repeatable. Given the same pseudo-random generator and the same seed, you get the exact same sequence of numbers. And perplexingly, this can be really useful. I mentioned that random number generators are used in video games and science. For science, they're frequently used for modeling things. So if you need to model a system, you will frequently have a whole lot of probabilities for things happening, and whenever you're working with probabilities, you will generate random numbers to test the probability. The repeatability of a PRNG is hugely valuable here, because it means that you can, for example, get an interesting result out of your model and write down what the seed was. And then you can run your simulation again. Or, even better, someone else could reproduce your study. Now, as we all know, they won't, but they could, and that's very important. The other extremely useful one, and probably the one that you all see more often, is in video games. Video games have got two things that are commonly randomly generated. Maps, so levels, and AI behavior. For levels, if you've got randomly generated levels, if you go back to any game that has them, for example, think Civilization, you will find that somewhere on the screen it shows the seed for the level you are playing. This is because if you get a level you like, you can replay it again and again. Or, more likely, if you want to play competitively, you can force everyone to play on the same level. This is good. For AI, it works to prevent a behavior that video gamers call save scumming, which is where you save before something difficult, try a whole series of actions, and if it didn't work, reload the save and do them again. You can avoid this by saving what your random seed was, so you can rerun the random number generator exactly the same every time someone loads a save. These are extremely useful. But in hand with repeatable comes predictable, right? And this is because, obviously, if you can take the seed and rerun the random number generator, I can take the seed and run the random number generator before you ever start. And then I get to look like a psychic magic man by telling you all the numbers that are coming out of your random number generator. I'm clearly a wizard and should win the lottery. This is actually a genuinely very real problem. Some pseudo-random number generators, particularly early ones, have very, very small what are called sequence times, basically how long it takes before the output starts repeating. And that means you can just write them all down. The LFSR algorithm, for example, generating random bytes, only generates 256 bytes, because that's all there are, but it generates them always in the exact same order. That means you can just write down all 256 numbers, you can point at the one you just generated, and I can tell you from then on exactly what number you're going to get and when. Now, this is not immediately obviously a problem, but, as I mentioned earlier, we use random numbers with security, with cryptography, all of the time. That means that any pseudo-random number generator that is easily predictable is totally unacceptable for use with security. If anyone does it, they deserve to be basically immediately fired. This is easier to do than you would think. There are random number generators in the Python standard library that are unacceptable for use with cryptography. Please be aware of it. For things like this, we define a subcategory of the pseudo-random number generators. And we have called it, because we are very inventive, intelligent people, the cryptographically secure pseudo-random number generator. This is a CSPRNG. It is one of the longer algorithms you will ever come across. And it is well worth remembering because you want, whenever you use random number generators, to look for the term CSPRNG before you use it. These are insanely more complex. They do all kinds of wacky bit shifting and XORing and applying hash algorithms and doing all kinds of bonkers nonsense. And so, of course, I'm not going to cover them. I can't walk you through an algorithm. But the kind of upshot of that is they are worth using, and my next talk will touch on them quite a lot more heavily. So, running out of time as I am, I'm running out of time to talk about random numbers, so I want to leave you with some questions to ask yourself, to think about, that will hopefully make you just a little bit uncomfortable. So, first one is, pseudo-random number generators in cryptography. How can it possibly be acceptable to use a deterministic source for building your crypto keys? Is it acceptable? Am I lying to you? If it is acceptable, when? When does it stop being acceptable? All of these things and more are in my next talk. Please come to it. But also, they are emphatically not in the Linux manual page. And please don't read the Linux manual page for random. Just ever. Don't read it. Next, If someone gives you an algorithm that they tell you is a random number generator, how do you tell if they know what random numbers it will generate? If you want a Google search for that question, you want dual, D-U-A-L, EC, DRBG. That's a fun Google search for you. It will open your eyes to all kinds of terrifying nonsense. And then, last one. If you're given a black box that is shouting random numbers at you, how can you tell the difference between a true random number generator and a pseudo-random number generator? Can you at all? All right, that's my time. I'll take questions from the room.
As this is our first question session, can I just emphasize that we want questions and not pseudo questions for the audience. So if you've got a comment or if you want to give your own opinion, people are probably more interested in hearing Cory's answers to your questions. So you could save those perhaps for the dinner tonight or another time.
Or come find me afterwards. Yep. I am happy to hear your opinions, but not while I'm stood in front of a whole lot of other people who will hold me to whatever I say.
Okay, so questions.
Cool, so I've covered all of randomness. That was good.
Well, so this session chair is supposed to have a few questions up their sleeve. This is the first talk I've been to where the speaker put my question on his last slide.
Yeah.
How are we doing for time?
Well, you can ask me to answer that question if you'd like.
So, Cory, I am talking to a web server. The web server is giving me back a random stream of numbers. How do I know that they know what they're doing?
Yeah. So the answer to that question is that you don't. You can know that they don't know what they're doing. So there are statistical randomness tests that you can apply to a sequence of data that basically say this is probably random or this is probably not. They're probabilistic, and they frequently will have false positives. And this is because it is quite easy to construct data that would pass a statistical randomness test that is not statistically random. It's not actually random, sorry. There is nothing that can be done about this. The reality is that randomness is not extremely well defined. Random output is best defined by its process rather than by its output. The process used to generate it, rather than the output itself. So unless you have access to the process, you cannot effectively validate it, which is fun. It's good to know that our security is built on that.
Any more questions from the floor?
Yes?
When is your next talk?
When is my next talk? Sometime on Sunday. I can't be more specific because I don't know. It is sometime on Sunday. There will also be slides online and a recording, so if you miss it, you'll be able to find it. And talk about Linux, it'll be fun.
Question for the front there.
You mentioned that iPhones have the chips in. Do other phones and desktops have them as well, or do they?
That is a great question. So they can, but mostly people don't talk about it the way that Apple talk about it. Apple are unusually open in this specific regard. You can get them, so the closest equivalent for desktop machines is called a trusted platform module, and they may or may not have random number generators. For desktops, you can buy a true random number generator built on top of free-running oscillators that will plug into your USB port. And you can use that as a source of random numbers on Linux, if that's a thing you actively want. I think you could probably write drivers for it for other OSs, but I haven't seen them. You can get one for $30. There's an open schematic on GitHub, I think, for that, and you can just buy them, little USB stick thingy. Or you could throw a whole lot of dice.
So there are more questions. Cory, can you unplug your laptop and can you come and get set up? Daniela, you had a question.
No, that's...
Okay. The question was, I am out of time. Thanks, everyone.